so, yeah, I'm very sorry that I cannot be there in person. Thank you very much for the invitation and for the organization of this very nice event. So the reason that I can't come to this conference, and yeah, it's really too bad, I was very much looking forward to it, is that I had a little hiking accident recently. So now I'm a cyborg due to this Titan plate here. And yeah, I'm still recovering, so I'm not very mobile yet. But yeah, thanks to COVID, I have the opportunity now to at least talk to you virtually. And I also have to switch to slides, so if there's some problem with the slides, so please just tell me. Okay, so I want to motivate what I'm talking about today by talking first about the cohomology of the modular space of curves. So wait a second. All right. So so this is connected to the modular space, to the cohomology of the modular space of curves and G. And to introduce this, I'm going to sort of start with explaining like the basics on what is known about this cohomology of this modular space. The basics are that we know what the virtual cohomological dimension of the modular space of curves is. So it's actually a 6G minus 6 dimensional space, but from the point of view of topology, it's 4G minus 5 dimensional. So that means that the cohomology groups vanish for all degrees larger than 4G minus 5. And that was proven by Hara in '86 already. And then there's a very celebrated and famous result on the stable cohomology of the modular space of curves. So we know that the cohomology stabilizes for large G, and the cohomology groups, they become independent of the genus at some point. And the stable cohomology is generated by a free commutative algebra. The generators are these kappa classes. And yeah, we also know the exact range of the stabilization. This result is due to many people. So just to mention a few names, maybe Hara and Mumford and Madsen and Weiss, but many others who contributed to this. And then there's another sort of older vanishing result on exactly the top degree cohomology groups that are known to vanish, at least with rational coefficients. And this is due to Hara and Charles Putman and Rita Sakazai, Zuki proved later. So to make up for not being there in person, I included some pictures. So I hope you can somehow see this and sort of see the details. I don't know, I hope it's not too small. Okay, I don't hear any complaints. So here's a picture of this cohomology. So here's this condition from the virtual cohomological dimension. So everything above this line here is 0 just by the virtual cohomological dimension. Then we have this dashed line here, which is the result of the vanishing result by Hara. And then we have this blue region down here, which is the stable cohomology, and this is completely understood. The whole gray area is not so well understood. This is the unstable cohomology of the modular space of curves. What is known about the gray area, or how you can gain some information on the gray area, is by calculating the Euler characteristic of the modular space of curves. And this is also the first aspect of the title of this talk. So eventually I'm also going to talk about Euler characteristics of graph complexes. But first I'm going to motivate this with a classic computation for the modular space of curves. So the true Euler characteristic of the modular space of curves, it's of course just the alternating sum over the Betti numbers. But there's another Euler characteristic that you probably also all know, the orbifold Euler characteristic, because the modular space of curves is an orbifold. And it's essentially some Bernoulli number. And this fact that this orbifold Euler characteristic is a Bernoulli number has been proven by Hara and Seguier in '86, together with the statement that the true Euler characteristic behaves asymptotically the same as this orbifold Euler characteristic. And by estimating these Bernoulli numbers here, can just write down sort of an asymptotic formula for these numbers. And this formula is just a constant. Then we have an alternating sign with the genus. So we have negative and positive Euler characteristics. And we have something which grows like c times g to the power of g. So we have a super exponential growth rate for the Euler characteristic for large g. And what this shows is, of course, that the total amount of cohomology in the modular space of curves grows super exponentially with g, because we have this factor here. And of course, the Euler characteristic also gives an estimate on the total amount of cohomology. And there's also a bit of extra information, namely that we have this alternating sign. So we also know that the Euler characteristic is often negative. And that means there's also much cohomology in odd degree. So there are many odd classes. So this is what we learned from this Euler characteristic computation. So back to the picture, what this shows is that in this gray area, so there are lots of classes, or in the whole area, there are lots of classes. There's lots of cohomology. And the first thing to look at is, of course, to the stable cohomology. So the obvious question is, can the stable cohomology explain these large amounts of cohomology? So looking into the stable cohomology, what we find is, of course, is at first a kind of disappointing thing, namely that there are no odd classes in the stable cohomology. So the odd classes always vanish. And the dimensions of the even classes, they are just the degree 2k graded part of this commutative algebra of these kappa classes. So each kappa 1 has degree 2, kappa 2 has degree 4, and so on. And the dimension of this is just the number of partitions of k. So that's quite easy to figure out. And then famously, this number of partitions, it grows with c to the power of square root of k. That's a famous result by Hardy and Ramanujan. So that grows like c to the power of square root k, and c to the power of square root k is not even exponential, it's sub-exponential. So the stable homology does not explain the super exponential growth rate of the Euler characteristic. And it also does not explain the huge amounts of odd classes that are predicted to exist by the Euler characteristic. So so what we learned from this is that the stuff that is here in this blue understood range, it's bounded by something that grows less than exponentially. So it grows like c to the square root of g. And so we don't really know still what generates all this cohomology. Okay, so this is the setup and this was actually the status still a couple of minutes ago. Is there a question there? No question? Okay. Sometimes I just hear echo, but so
you know, maybe we don't always hear you very well. I don't know, maybe you are approaching or getting further from your mic. Maybe check how your position, because sometimes we hear you well, but not always.
I see. Okay.
Well, now it's good.
Okay, so I try to maybe get a bit closer to my picture.
Yeah, and don't move.
Okay, I also cannot hear you, so it's a mutual problem, unfortunately. Can you say again? There. Okay, I just tried to. Okay, but please tell me if the problem persists. Okay, so there are a couple of explicit computations, and they go up to G equal to 4, and they are by a couple of people. So the most demanding computation was by Tomasi in 2005. And she also proved the existence of the first known odd class on the modular space of genus 4. So that was the only known class before 2018. So these are these explicit computations, and of course they don't really shine that much light into the whole situation because they are in pretty low Gs and cannot tell us that much about it. The whole situation was changed in 2018 by a paper of Changelacius and Payne. And I briefly want to talk about this Dedekind weight filtration on the cohomology that is necessary to formulate this result properly. But I'm not going to talk about it, or I'm not going to use it that much. So if you're not interested in this, yeah, that's no problem. So Dedekind defined this weight filtration on any complex variety, and it's a refinement of the usual singular cohomology. And so we have this filtration by W naught until W of the kth cohomology group, and the weight L graded piece now is the quotient of the WL over WL minus 1. And this quotient is pure Hodge of weight. So that's the point. So the result of Changelacius Payne is now that the top graded piece of the cohomology of the modular space of curves with some degree shifts here, so some dualization actually, is isomorphic to the cohomology, to the graph homology of the commutative graph complex. So we have new information now, thanks to this work. And so what is this commutative graph complex? So that already appeared in Francis' talk yesterday and also in other ones. So I'm briefly going to flash the definition again. So the even graph complex GCG is a Q vector space, first of all, that is generated by all isomorphism classes of pairs of a graph and some labeling of the edges of the graph. So this graph gamma is connected and of rank G. And the requirement is that each vertex has degree at least 3. And the labeling of the edges just gives sort of a projection of the set of edges to the integers 1 to n. So n is the number of edges of the graph. And so this graph complex is now the Q vector space that is generated by all these isomorphism classes, not the relation. We are allowed to include the edges, but we have to acknowledge all the sign changes. So if we switch the order of the edges, we pick up a sign for every transposition of sign. So the grading of this graph complex is defined now in my talk in terms of the number of edges of the graph. The chain groups are given by all graphs with k edges. And the support just by combinatorial and by implementing this restriction to all graphs where the vertices agree at least 3. it gives these kind of constraints. So k is smaller than g plus 1 implies that the graph has too little edges to actually have rank g. And k larger than 3g minus 3 implies that there must be at least one equivalent vertex. And then there's this differential that just maps one of these isomorphic classes to the sum of all edges, and we alternate with the sign depending on this. So here's this picture, this basic picture of the graph homology. Did you?
I'll just
It's here, or this is his?
Okay, there's a technical problem apparently. Can you still hear me? Okay.
No, yes.
Okay. That's good, doesn't it? Okay, so we'll start again. No protests. So this is this picture of this naive picture just by the combinatorics. We see that this homology of this graph complex, it has some yes, it has support like in this gray wedge here. And yeah, so below here, everything vanishes because the graph doesn't have enough edges. And below here, everything vanishes because the graph has too many vertices. So what's the non-trivial knowledge on this graph complex? And this is mainly due to Thomas, namely that we have a stabilization result, first of all. So the graph homology vanishes below a certain line. So for k smaller than 2g, there's no homology in this complex. And then most importantly, and also especially for this conference, of course, there's a certain diagonal of the homology that is isomorphic to the Grothendieck-Teichmüller Lie algebra. And so this is in the context of these estimates of the amount of homology or cohomology of the modular space of curves. What is then very interesting is that there's an injection of the free Lie algebra, which we also heard about yesterday, in generators in odd degree into this Grothendieck-Teichmüller Lie algebra. And it follows from this by a quite basic argument, just by estimating the Poincaré sequence of this free Lie algebra, that the dimension of the homology groups on this diagonal, it grows exponentially for large enough G. And what we also know about this graph complex is quite some impressive explicit computation on its homology. So this is the picture. This purple line here is this Grothendieck-Teichmüller Lie algebra that injects into this, or that is isomorphic actually to this diagonal. And then we have this injection of this free Lie algebra. And the generators of this free Lie algebra here are depicted here. I mean, they are classes, and I depict them here as these purple dots. And in total, they give them like an exponentially growing amount of homology in this graph complex. And these orange classes here, they are explicit computations in low rank. And again, we have the stabilization here that the blue region has just vanishing homology. And yeah, so this is this result by Thomas, that this purple diagonal given by this equation here has all these classes associated to the Grothendieck-Teichmüller algebra. Okay, so we can go back to this result of Chan-Gales's-Payne that identified this top weight cohomology of the moduli space of curves with this graph complex. We can also think about it if you don't like this Deligne weight filtration, just as an injection of this homology of this graph complex into this into the cohomology of the modular space of curves. So we can take this picture and just map it onto the cohomology of the modular space of curves. So this is the homology of the graph complex, and we map it onto our picture for the cohomology of the modular space of curves. And what we see is that this pink wedge here, this represents exactly the image of this injection. So the pink wedge is now where this graph complex, this even graph complex, maps to in the cohomology of the modular space of curves. And we also, interestingly, now, of course, get this super exponentially growing line of cohomology groups, which live here right below the top degree, because the dotted line, recall that the dotted line vanishes by this result by Hara, but right below we find now this exponentially growing family of cohomology classes thanks to this result, thanks to this chain of results by Chan-Gales's-Payne, Thomas Wilracher, and Francis Brown. And we also win a couple of classes that are due to explicit computations. And yeah, so these classes, these explicitly computed classes, they also give like new classes in odd degree. A problem, I mean, slight caveat here is that all these classes here on this line, they are in even degree. And this also proves that we have now at least an exponential growth rate of the cohomology of the modular space of curves, namely here on this line. And this improves the situation already a lot with respect to this estimate here, thanks to Hara and Sergei, on the total amount of cohomology in the modular space of curves. So there's much more cohomology on this line than in the stable cohomology. So yeah, so this is our review sort of still. Yeah, so what's also still, what I still should mention is that there's an extension of this result by Payne and Wilracher from last year. And they actually prove the existence of many more classes by injecting into the next to top weight degree in the weight filtration. And the picture then changes even a bit more. And we find like new exponentially growing families of classes. And they are exactly these kind of orange classes. I don't know if you can see them, but there's like 9 new lines now, thanks to this result by Sam Payne and Thomas Wilracher from last year. So they also extend like in the same diagonal direction in this diagram. And each of these 9 lines here grows, gives like more than exponentially much cohomology. What's interesting there is that all these computations also touch like only this image of the initial map. So it does not extend beyond this purple wedge. So everything seems to only play like in this purple wedge so far. But yeah, so that's just a remark. Okay, so that was now the review part. The question that I want to address now is how much of the modular space of curves cohomology can be possibly explained via this argument, by this graph complex. So how much of this initial problem here by Hara and Sergey can be explained by homology that is injected into this red wedge? And the basic idea is to replicate this approach by Hara and Sergey onto this graph complex. So the idea is to estimate the amount of graph homology just by computing the Euler characteristic of the graph complex. Yeah, so the Euler characteristic of this even graph complex is of course also just given by the alternating sum over the Betti numbers. And estimating these numbers, of course, also gives an estimate on the total dimension of the homology groups. Actually, there have been many computations of this Euler characteristic before. So there have been a computation by Wilbacher and Marko Zivkovic, then a computation by Zugmene and Turchin in 2018, and then there has been another calculation by Chan, Faber, Gelasius, and Payne, 2019. All these computations, they have different characteristics, and they also compute like different generalizations of this Euler characteristic. And interestingly, they also give like all completely different formulas for this Euler characteristic. Unfortunately, none of the formulas that have been obtained is directly applicable for an asymptotic estimate of this number. So this is the new result. So there's a new formula, another fourth formula, so to say, for this Euler characteristic. And this allows to actually estimate the asymptotics, this new formula. And I also should mention that there's a similar formula that was proven by Don Zagier in 2008. And he used actually this result by Chan, Faber, and Gelasius and Payne as a conjecture. So it was conjectured, I think, by Faber, or no, I think it was conjectured by Zagier himself. And he proved this simpler formula, but this was hidden in some unpublished notes, and they were quite hard to obtain. So then I figured out that I actually rediscovered this formula by Zagier. All right, so how do you prove this? So what was my approach to prove this formula for this Euler characteristic of the graph complex? The basic approach is quite obvious. What you have to do is you have to count the dimensions of the chain spaces, so the number of graphs that contribute to each of these chains. And there's a very cool framework in which you can perform these kind of computations set up by Gessler and Caprano in 98, which is dubbed sort of this theory of modular operands and Feynman transforms. What I found useful while working with this is also that this can be interpreted in this categorical formulation of combinatorics by Joyal in this theory of species. So yeah, you can reinterpret this more combinatorially in terms of species. And but still a key step remains for this computation, for the simplification. And this key step is to formulate everything. So formulate this formula in a quantum field theory-ish kind of integral expression, which you can evaluate. So this is like a essentially a Gaussian integral. And yeah, you can evaluate this using like asymptotic analysis. Yeah, so a similar computation has been performed by Gessler and Caprano for the associative graph complex, which I'm not going to talk about, but you might know it. So it's a graph complex that also computes the homology of the modular space of curves, but the modular space of curves with punctures. So it's a related construction. Yes. I'm just going to flash this formula, so I'm not going to go through it in detail. Just because I have the opportunity. So this is the formula that you can use to actually estimate the asymptotics of this Euler characteristic. There's like the Bernoulli numbers appearing in there, and they are also responsible again for this large growth rate that's going to pop up. So I just wanted to focus you on this part here because it's quite interesting. So this is the number theoretic Möbius function that appears there. And this is a formula for the Euler characteristic of the commutative graph complex. And there's an old calculation by Gessler and Kapranov from 98 on the Euler characteristic of the associative graph complex. And to translate between both these computations, you just have to switch the you just have to switch this Möbius function down here with the Euler-Toschen function. So this is really like a very similar formula for those completely different objects. And if you have some explanation for this phenomenon, please tell me. I would be very interested. Okay. So the main result, the main theorem then is the estimate of the asymptotics of this Euler characteristic. And interestingly, you get a parity phenomenon. So for even G, the Euler characteristic behaves differently than for odd G. And the difference is actually quite extreme. So for even G, we find again like a constant, an alternating sign, and something that grows super exponentially. So there's a constant times G, and this whole thing is taken to the power of G. For odd G, the situation is a bit more involved. So there's also a constant, but then there's a term that is heavily oscillating. So there's a sign, and in the argument of this sign, there's a square root of pi times G. So it's quite easy to see that this term here, I mean, I hope you can see it. The contribution for each G larger than 2 is definitely irrational. And it's also irrational mod pi. So this is never going to vanish. And it's also not going to have like any periodicity up in here. So it's very, so the magnitude of this Euler characteristic oscillates quite frenetically. And then there's a term that goes like c to the power of square root G. And then there's some term that goes like g to the power of G over 2. So in total, we also have super exponential growth here. So the proof of this follows from an analytic argument. I just want to give like some, so as a consequence of this, we also can estimate this Euler characteristic. And the estimate is just that for even G, we have the Euler characteristic being large, so it grows super exponential. So it's like G to the power of G. And you always have to include some fine print. So there exists this constant such that this only holds for large enough G. And for odd G, it grows also super exponentially, but not quite so much, because we have c times G to the power of G over 2. So this is this estimate. So I just want to mention like one amusing result one amusing part on how to use this estimate or this asymptotic equation here to prove this estimate. So what is amusing about this is that you need to estimate this very oscillating sine function, and we have this irrational argument here. And so normally that would be hopeless to estimate something like this, but thankfully the irrational constant that lives in here is pi. And people have been working quite hard to actually evaluate the irrationality measure pi. So there are very good bounds on how pi can be approximated by rational numbers. And using these kind of bounds, one can actually prove that this oscillating part, it fulfills a lower bound. So even though one might naively think that this oscillating part might make the Euler characteristic vanish at some point, because this argument can get very close to the multiple of pi. This is not the case thanks to these irrationality measures. So the short result is then that we have like an exponential, super exponential growth rate for this Euler characteristic for even and odd G. And I also want to mention like a related computation for out Fn, the outer automorphism group of the free group. So there we can also estimate or compute the asymptotics of the Euler characteristic. And similar to the Hara-Zaghir result, we can also relate it to the virtual or the orbifold Euler characteristic of out Fn. And what we get is that it's just proportional, so that the ratio tends to a constant. And we also have like a value, an asymptotic expression like for this Euler characteristic. This is upcoming work with Karen Vogtmann. Yeah, so in terms of graph complexes, this also computes the Euler characteristic of the so-called Lie graph complex. And I just want to mention that there's like more complicated techniques required to do this, because the Gessler-Kapranov technology is not quite sufficient to get like a good formula for this Euler characteristic, unfortunately. Okay, so for the rest of the talk, I briefly want to, of course, go back to the graph complex and its homology, and also the modular space of curves. So going back to the graph complex, so here we have this this red wedge, and by this result, what we know now is that in this red wedge here, there's like super exponentially much homology hiding that we don't know about. So this line here, it explains exponentially much, but actually there's super exponentially much homology in here. And this is also interesting because it disproves some conjectures on what kind of Lie algebras might generate all these classes that are hiding in here. The same result can now be just transferred to the modular space of curves by the result of Chan-Galash's pain. Namely that if we restrict ourselves to the top weight degree cohomology group, to the top weighted part of the cohomology groups, then we also find super exponential growth in only these top weight degree parts. So they are super exponentially classes in this top weight graded piece, or in these top weight graded pieces. And there are also many odd classes, because both these Euler characteristics, they are oscillating quite widely. So going back to this picture of the modular space of curves, what we find now is that we find by this injection of this graph complex into the cohomology, that there's super exponentially much cohomology in this red wedge. And so if you look exactly into the growth rate of the cohomology, you can see that it scales with g to the power of g, or g to the power of g over 2, depending on the parity of g. But by the Hara-Zaghir result, we have a scaling of g to the power of 2g of the amount of cohomology, the total amount of cohomology. So we explained a bit more. So this red wedge here is now, the situation is a bit better. So only in this top weight graded piece, we already find like some super exponential growth, but it does not account for the complete growth rate that is implied by the Harazagir result. And yeah, the obvious questions is if we include like these lower weight graded pieces, if everything is maybe concentrated inside this red wedge somehow. So if we can sort of get stronger results, stronger bounds, for instance, by using this newer result by Wilwacher and Payne, to also estimate like the amount of cohomology in the next to top weight graded pieces or the lower weight graded pieces. Okay. Yeah, so that's it basically. So I still have a couple of minutes, I think. Or don't I?
Yes.
So briefly, I also just want to talk about the odd graph complex as a little bonus. So there's also an odd version of this even graph complex. It's defined similarly. You just change this condition that graphs, that this marking and this relation between graphs from essentially edges to vertices and the orientation of edges. So this odd graph complex, it's generated by isomorphism classes, triples. We have a graph, we have an ordering or a labeling of the vertices of the graph, and we have some orientation on the edges. So each edge comes with a little, each edge is directed. And similar to the even graph complex, this graph complex is now the Q vector spaces by all such pairs. And the relations are now that the sign is supposed to change if we transpose two vertices. And the sign is also supposed to change if we flip the orientation of an edge. So this is a new convention to an alternative convention to define such a graph complex. And this is called the odd graph complex. The grading is now here defined in terms of the number of vertices. And the support is a bit changed. So in this grading, because I mean, we are not allowing like graphs with 0 vertices. And we also don't allow graphs with 2 valent vertices, so get different bounds. And the differential is also defined analogously. There's also much information on this odd commutative graph complex. I don't know that much about it, but I think that there's also this diagonal here. This actually is the top degree part that is isomorphic to the space of finite type invariants in knot theory. And I think this is due to Barnard-Hahn. And there's also many other facts about this graph complex that I don't mention. So I think also like other diagonals also correspond to other invariants, like for other types of embeddings. What I just wanted to mention still is that you can repeat this Euler characteristic computation for this odd graph complex. And what is interesting about it is that the Euler characteristic behaves very similar to the Euler characteristic of the even graph complex. So if you take like both generating functions of the even and the odd graph complex, and you add them up in this way, I mean, this is very related to this just sort of computes the yeah, essentially this just gives like the graph complex of disconnected graphs, which is very related. And if you add them both together, you find something that is very simple. So the generating function of the sum is just given by the log of these kind of necklace polynomials here. And we have this, we divide them by z to the power of g, so they are somehow normalized. It's a bit weird, this generating function, but it's very simple, so I wanted to show it. And of course, what would be very neat is to somehow plug together the odd and the even graph complex such that most of the classes cancel. and obtain a complex whose Euler characteristic is somehow generated by this stuff here. Maybe such a formula can help like guess how to plug together like both even and odd graph complexes. And yeah, so if you know what kind of complex could be could have an Euler characteristic that is generated by these kind of objects, then please tell me. What also follows from this is that the Euler characteristic of the odd graph complex is just asymptotically the same as minus the Euler characteristic of the even graph complex for large G. So so that's what I wanted to tell you. And here's the picture again of this on this map of the cohomology of the modular space of curves. Thank you, and yeah, I wish I could be there.
The questions. Questions? I think, Michi, your talk was so incredibly clear. You already answered everybody's question. So, there's a question here.
Could you just say a few words about the implication for the Libra complex of the Euler computation? We have similar qualitative outcomes about all dimensions.
Unfortunately, Francis, I think you have to repeat the question to me because I cannot understand it. Maybe it's in the back of the room and the microphone is not working.
It's complicated to understand.
I'm just wondering about the implications for the Lie graph complex of the Euler characteristic computation that you just mentioned.
So the question is, what are the implications for the Lie graph complex of the calculations you just mentioned? Am I facing on one?
No,
Sorry.
I think it captures that's the mic, right?
The mic is there. Oh,
The mic is here, the camera's here.
Yeah, you just need to speak a bit louder. That's it.
Did you hear the question?
Yes, so I think the question was what the implications on the Lie graph complex are of this computation. So I mentioned that there's another computation on the Euler characteristic of this Lie graph complex by together with Karen Vogtmann. And a priori, the implications of the even and the odd graph complex on this Euler characteristic of the Lie graph complex are nothing. I don't know of any concrete applications. There are some construction based on cojoule duality, because the Lie graph complex is cojoule dual to the odd graph complex, let's say. No, to the even one. And for instance, there was a paper recently by Ben Ward to transfer some classes from the Lie graph complex into the even graph complex, or vice versa. So there could be some connections, but I don't know of any application of these Euler characteristic computations that survive somehow these kind of cojoule duality arguments.
My question is about the last part of your talk about the odd graph complex.
Yes.
The homology of the modular space. So even one is known to be related due to chain the lattice space. What about the odd one?
Sorry, so there was the last part of your question was not very audible. Sorry. Could you maybe change your position a bit?
Can the homology of the odd graph complex
Yes.
projected to the homology of MG?
If there's a relation between the cohomology of MG and the odd graph complex, is this the question?
Yes.
Yeah, that would be very interesting. I can say that there's that the odd graph complex, there's a relationship between like some relative homology of out of n and which sort of lives in this Lie graph complex space, and this odd graph complex. And one can maybe think about if one can somehow construct like a relative, if there's some relative cohomology of the mapping class group or of the modular space of curves that corresponds to the homology of this odd graph complex. Yeah, that would be very interesting. Maybe also some twisted cohomology, because in the context of out of n, this appears if one takes the cohomology with with some twist to the coefficients. So then you can recover the odd graph homology.
So I have one question, so you're saying that you can get these asymptotic Euler characteristic formulas for the Lie, associative, and commutative operands. Can you say in general, if you start with a cyclic DG opera that you understand very well, when can you expect to be able to calculate such an integral formula for the asymptotic Euler characteristic of the Feynman transform?
Yes, so this is the work of Gessler and Capranoff. So if I understood the question correctly, this general formula applies by Gessler and Capranoff. It applies for the even and the odd graph complex. They are not very. Huh? Can you still hear me?
Now we can. Your answer was fully out of our reach. Can you say? Can you talk again? Sorry. Okay.
So if I understood the question correctly, so the Gessler and Capranoff theory, it allows to compute the associative graph complex, the Euler characteristic of the associative graph complex, and the Euler characteristic of the even and odd commutative graph complexes. I think they didn't quite appreciate that you have to change like these two parities, so the odd and the even one. But the Lie graph complex is not so easy. It does not really work.
I think the Wi-Fi won't start as much. I think likewise. Perhaps Michi can respond.
I keep disappearing. Yeah, so sorry, so should I repeat the answer?
Okay, let's try one more time. Thank you very much.
Yeah, very briefly, I mean, what about? Okay, sorry. Okay, I will try again. So the answer is that the even and the odd graph complex and the associative graph complex can be computed in this framework of Gessler and Capranoff. The Lie graph complex is more complicated. So everything only applied to the Euler characteristic. So yeah, so in this Gessler-Capranoff language, it's not so easy. But yeah, so I'm very sorry. I wish I could be there. And yeah, if you have any questions, just email me, or we can also Zoom. So yeah, I'm happy to answer questions in another way. So this way it's a bit complicated, unfortunately. I'm very sorry.
Okay, well, thank you very much.